Okay, I will call
Yeah. I think it's okay. Yeah, I can hear myself. Yeah, maybe it's too close even. Yeah. Okay, so thanks. So this is my final lecture. Thanks all for coming on a late Friday afternoon. I won't keep you too long, or not past 7 anyway. So in the first lecture I introduced surjective submersions, in particular as a technique to do concrete calculations with integer cohomology classes. And in general, surjective submersions are much more useful for that purpose than working with open covers. And in particular, the reason I was interested in this has to do with T-duality. So last time I started introducing T-duality. So let me just start where I took off. Where I left off. So I described T-duality as a sort of an inversion in circles. Radius 1 goes to 1 over r. And I argued that there exists a generalization for which the setup is circle bundles, so principal circle bundles. In fact, you can generalize it even to tori and other spaces, non-principal bundles. And the data in such a setup are the isomorphism class of a circle bundle. So that's given by an element of the second cohomology group, integer coefficients of the base space M. So let me call an element in there F. The F stands for the curvature over the round representative. And the other thing that goes in here is a 3 class on the bundle, which is called an H flux, which is the curvature of what physicists call the B field. So I argued that if you do T-duality, that the dual of such a situation is again a principal circle bundle, but in general one that is not isomorphic to the original one. So again, it's given by sets of data f hat and h hat, and they're related by the fact that if you push forward the h field or h curvature here to the base, so you, in terms of differential forms, is just integrating over the fiber. You get a two form, or if you do it in check cohomology or in submersion cohomology, you get a two class with integer coefficients. And this situation is symmetric in the sense that if you do the same thing for the dual bundle with this corresponding dual h field, you get the original curvature back. Now I said that doesn't determine h hat given f and h, and what I told you that the procedure is to look at the correspondence space so there's two projections. The projections here are just one tensor pi. Let's call it p hat, and here pi tensor 1. Let's call it p. And there's little p's and big p's, so sorry. And the condition is that if you take the h here and you pull it back, and you subtract the pullback of h hat, this should be 0 in the cohomology, in the third cohomology of the correspondence space. And I claim this essentially uniquely defines what h hat is. Okay, so I gave you an example of how you use this for, say, circle bundles over a two-sphere. So I won't repeat that. But what I want to do is maybe give you some intuition where these formulas come from, or another way of interpreting them. And this also allows you to generalize this setup to possible other situations. So the interesting thing for circle bundles is that you have an exact sequence called the Giesen sequence. So the Giesen sequence is an exact sequence in cohomology. So let me write down a few terms. So if you start with a form or a check class or a submersion class on the bundle space, you can push it forward, so integrating over the fiber in the case of forms, and then you can, well, plus 2. This map is the easiest, k of m to hk of p, that's just the pullback. The connecting map in this exact sequence is taking the cup product with the class of that defines the principal S1 bundle. So if I have color, I can now do something nice. So this sequence is determined by f, so by the isomorphism class of your principal U1 bundle. And if you apply this to k equals 3, nobody warns me that I'm making an error here. If I integrate over the fiber, I go to k minus 1, so here I go to k plus 1. Okay, so if I apply this to k equals 3, got 2 there, 4 there. So my H flux is sitting in here. And I claim that if I push it forward, I get f hat. So f hat is indeed a 2 form on M. Now f hat, since it's a 2 class on M, it defines a dual bundle or an isomorphism class. So I can also look at the corresponding sequence for the dual one, the bundle defined by the dual flux. So that is given by the cup product with f hat here. So f is sitting in here. And now the nice thing about exact sequences is if I apply the map twice, I get 0. So f hat cup f is 0 in cohomology. But that means that here it's also 0 if I map it over here. So this f has to come from something over here, which is what is called h hat. And that, of course, is, well, those are those two relations. But that h hat is, of course, not unique. It's unique up to some term that comes from here. And that you can fix by putting that condition. So it's a bit of a diagram chasing. You can put this into a double complex and then diagram chase that indeed this fixes the h hat. Okay, so Giesen sequences also exist for not just for the one sphere, but also for well, they exist for all spheres. But for instance, the three sphere is an interesting case because the three sphere is both a sphere as well as a group. So you might think that maybe there exists some duality analogous to this one for three spheres or for SU2. And I won't be talking about it, but we started investigating this and we call it spherical T-duality. Well, I think it's still open whether this is actually useful or not. I mean, topologically you can do it, but whether you can also do it on fields remains to be seen. So if it's relevant to anything, it should be relevant to M theory, because it corresponds to different fluxes of higher dimension, and these are precisely the fluxes occurring in M theory. Okay. So I want to see how this, to actually relate this a bit to Fourier transform. I want to see how this acts on the fields. And, well, this should of course be derived, but if I give you the answer first. So, of course I can decompose invariant fields such as the three form H. Well, this is what I did yesterday for the case where P equals M cross S1, and then I derived a T-duality on forms over here by decomposing that in their components on M cross S1. But that you can do for non-trivial bundles as well, but you need a connection. So these F, so locally I can write F as the D of a connection, and then I can write H, this three form on P, this is if the form is invariant, as a three form on the base plus a wedge, a two form on the base. So this is sort of a generalization to non-trivial bundles. Yesterday I had the d theta, which is the trivial connection, or the connection on the trivial bundle, but you can do this more generally. This is called Chern-Weil theory. Okay. Similarly, I could do this for f hat, write it as the d of h hat, and h hat. So it turns out this component is the same for h and h hat, but yeah, they differ like that. Okay, so.
Is there a connection or?
Sorry?
One
Yeah, so one. It's a connection. Sorry, connection one form. Sorry?
Connection in the one form, and that is the.
Oh, you mean the connection like so? It's a well, it's a connection one form on a principal bundle. So which satisfies the usual conditions for principal connection. Now you mean by connection something which is D plus A, maybe. Is that the confusion, or?
Well, intuitive level, we have a natural connection. In general, the connection by F.
So on M, a connection is written as the Maurer-Cartan form. So in this case, it's just d theta plus something on the base, where this satisfies the usual transition function on overlaps. Maybe I'm using the, oh yeah. So the T-duality is just replacing H2 goes to, well, H2 is the F hat, and the, well, this one, the H2 hat, sorry, H2 hat is F. So that's how T-duality works here, and you indeed see that H minus H hat, or H hat minus H, sorry, I have the signs, if I have the signs incorrect, but this is indeed a exact form, as it should be. And of course, in this notation, I've left out all the pullbacks, etc. I mean, everything's on the correspondence space. The reason why I'm writing this is now I can give you the analog of my isomorphism between cohomologies that I derived in the trivial case. But in this case, it's not an isomorphism of integer cohomologies. So what you need to do is, well, so I claim I have an isomorphism of, say, Z2 graded complexes, invariant forms with a differential, which is now a twisted differential. So the twisted differential is given by D plus H wedge. So that acts on Z2 graded cohomology. Yeah.
So why is H3 the same? Is that an assumption?
So I haven't told you where this comes from, which I'll do later. But this is the. So I have to tell you. I mean, I have to derive T-duality on forms, and it turns out this is the outcome locally. Now, the topological information in this is precisely what I've just erased. What comes out of the Giesen sequence. But this is a computation that these components don't differ. But intuitively, T-duality should be doing something on the fiber, on the S1. So what sits completely on the base space should not really see that T-duality. So that's why these components have to be the same. Okay, so twisted cohomology. So this adds a degree 1 to the form, this adds a degree 3, so it's on Z2 graded cohomology. And, well, I claim the formula is just this. It's just E in the power A wedge A hat, same A and A hat as over there, times omega. So this indeed is exactly the same form as I had before. Before I had a d theta wedge d theta hat in the case of the trivial S1 bundle. In case of the non-trivial S1 bundle, you get this factor, but you see that that precisely implies that if I intertwine it with the twisted differential, that it flips the twisted differential with respect to H to the twisted differential with respect to H hat because of this relation. So again, this formula that looks very much like a geometric analog of Fourier transform. Now, twisted cohomology is in general not perhaps that interesting. It's usually quite easy to compute, but it's it's only non-trivial in specific cases. Really the interesting case is to do this on K-theory. So it turns out that this map is then an isomorphism of what's called twisted K-theory. I'm not going to go into that. Twisted K-theory is something which supposedly classifies d-branes, or charges of d-branes. So if T-duality is a genuine symmetry of the theory, of string theory, it should be an isomorphism. There should be an isomorphism between the d-branes and the theory. So that's the K-theory analog is that as a manifest of that. Okay. So what I'd like to do now is derive these formulas, or to tell you how to derive them. Probably. So these formulas are, or these collection of formulas are called the Buscher rules. So they can be derived from a sigma model formulation of string theory. So, I mean, I've just given you the simplest case where I just look at like a circle bundle and only a background B field to which the string is coupled. In principle, T-duality should be a symmetry of the whole string theory, so you should be able to find these transformations on all massless fields or even all massive fields. So, for instance, Ramon fields also transform on the T-duality, etc. I've just presented you the main, well, the basic case. So you derive these transformation rules, these T-duality rules, from a sigma model action. So let me take the simplest case where of a closed string on something which is locally a manifold across a circle. So X is my closed string field. So mapped from sigma into space-time. And then the sigma model action is something like d sigma d tau, where tau, sigma and tau are local coordinates over here. And then typically they're coupled to a metric on the world sheet. So alpha beta is the coordinates, well, maybe I should call them sigma alpha, but those are the coordinates on the world sheet. Let me call the coordinates on the space-time M and N, capital M and N. So the sigma model action is something like this. This is the coupling of the string field to the metric. And, well, there's a coupling to this B field, this 2 form. And this is all local. And, well, there can be coupling to other fields like the dilaton, etc., or the Ramon fields, or whatever. So I'm taking M to be locally something like, well, U cross S1, or even U cross maybe a torus. So a torus bundle. Okay, so in order to do the calculation, you can simplify it somehow. You can use the two-dimensional conformal invariance to bring this worldsheet metric into a diagonal form. And then you can combine G and B, and you can go to complex coordinates, whatever makes things easy. So this is in complex coordinates, where Q is just G plus B. Okay, so I'm looking at things which have symmetries on the action of S1 or Tn, and I'm assuming that my action is invariant under the symmetry. So if that's the case, you can choose local coordinates, xm, so let me call them well, what do I do here? Mu and xm. So these are the coordinates along the torus, and these are the coordinates on my base. I should not have called this m, maybe I should have called this p. But these are the coordinates along the base, m. And then my invariance is the statement that locally on the translations of x, this action is invariant. So that means that your q only depends on coordinates on the base. Okay, I don't know if people see where I'm going, but if you have an invariance, this is a global invariance. This is an invariance under shift by epsilon, which are global, but whenever physicists see global invariances, they want to make them local. So you make them local by introducing a gauge field. Anyway, so yeah, so what I want to do is introduce a gauge field. So a gauge field AM on the world sheet, and then replace the ordinary derivatives by covariant derivatives. So dxm plus am. Okay, so I claim that if you do that, and you write out this action, well, you decompose the q's into the different directions, mu and m. So you have a term here on the base. So this is a bit of writing. This would have gone better and quicker on slides, but well, so in the direction of the fiber, I replace them by covariant derivatives. Sorry, I'm skipping a term. This is completely trivial, but of course I have to mess it up. So this is the same action as that one, except that I've now replaced the ordinary derivatives by covariant derivatives in direct direction of the torus, in direction of the fiber. And then you add a term with an auxiliary parameter. And this term here is just the curvature of this gauge field, which you've added. And what I claim is that this action is actually completely equivalent to the action I started with, but this has a gauge invariance. This has a gauge invariance, so an invariance like x plus epsilon, where epsilon depends on the worldsheet coordinates, and the variation of this action with respect to that variation is compensated by the fact that you have introduced these gauge field, which transform in an appropriate way. So I guess I don't want to write out the whole thing. I just want to say how you now get the T-dual. I mean, this is a well-known calculation which you can find in any review on T-duality.
The last term, how are the indices saturated? You have D and D bar. It's supposed to be a 2, no, I mean the last term, the last line. It's supposed to be a 2 form of, so you integrate over x hat.
I integrate over, yeah, into the path integral I would introduce another field x hat that I integrate over.
Right, which sets dA bar equal to d bar a.
dA bar minus d bar a. So that's the curvature of a in complex coordinates.
And then, so you claim that this is the original action.
No, it's not the original action. It's equivalent to the original action. And the way you prove that is by integrating out the auxiliary field, which puts the curvature to 0. And then you can just choose a flat gauge and just gauge fix, and then you go back to that action. But there's a different way of doing it. Rather than first integrating out the auxiliary field, that's why I put in this term to put the curvature to 0 to make everything trivial. There's a different way of doing things, is by integrating out A first and then gauge fixing. If you do that, you get a different action, but it has that same form, with a Q hat which is given by, well, so it's given in components, and so these formulas are a bit unwieldy, but so on the base you transform Q to this. On the components which have one component in the base and one component on the fiber, transforms like this. So these are the T-duality rules for the torus locally. And again, the way you derive them is by taking an action, gauging the global invariance, adding a gauge fixing term, or adding a term which puts the curvature to 0, so that this action is actually equivalent to the one I started with. By integrating out the auxiliary field, I get the curvature putting to 0, I choose a flat gauge, and then gauge fix. The other way around, if I integrate out A first, and then gauge fix, I get an action which looks the same but with a different Q. Now you can argue that that's actually a symmetry of the quantum theory as well. And this is called T-duality. Now these formulas still look a bit complicated. Let me write down what it means on the circle, which is what I've restricted myself to anyway. So remember that Q was G plus B, so this formula has both G and B in it. So if you restrict this to a circle, so just one direction, you find that the G hat, so just do one direction, so let me call theta the coordinate in S1 direction locally. So you find that the theta component of the metric, so this is in the dual circle, or maybe I should say that what I'm doing here is, so this action which I just erased, this gauged action, is actually an action locally on M cross S1 cross a dual circle, where this was the coordinate x and this was the new coordinate that I've introduced. So I'm actually doing like precisely this correspondence technique that I did topologically as well. So this is the simplest formula, and this just tells me that R goes to 1 over R. So this is indeed correct. Well, okay, so you have formulas for G, for all the components of G and all the components of B. And maybe are there in the notes, so maybe I won't write them out. But essentially what you see is that certain components of G get interchanged with certain components of B. And this is exactly what the global formulas did tell me. These components of G for a principal bundle are given by components of the gauge field. So the gauge field gets interchanged with components of the B field. So that's exactly the formula that, well, this will lead to the formula that F hat equals pi star of H. So again, I'm not going to write down all these formulas here, but what you can do is analyze them for a metric, which is a metric, so a metric on the principal bundle, which canonical metric is a metric on the base, and a metric in the fiber direction is given by your gauge field. If you write out these equations for that particular situation, you can see that although I've written down things locally, they patch to some global transformation, and that transformation is precisely the one over here, as well as the other things like the transformation of age, which I've, which I've erased, but that formula contains the fact that the component on the base here is the same as for the original situation. I forgot who asked that question, but that follows from these relations. Okay, so yeah, okay, so if I do this for the metric of this type, these transformation rules will give me the transformation of H, so it will give me a formula for H hat, it will give me a formula of B hat, it will also give me a formula for F hat and its connection H hat. Now, with a little more work, you can also get the rest of the Deligne class. So remember that I put everything, well, that I put bundle 0 gerbes or line bundles, that I was interested in three components there, which was the curvature, the connection, the gauge field, and the transition function. And that for a bundle 1 gerbe, I was interested in the 3 class H, B, and then a 1 form C, and a transition function H. So with a little more work, you can also get the transformation rules for these other guys. But yeah, I have no time to get into that. But but this is T-duality. This is sort of the differential form, or the differential T-duality, people call it these days. And again, this is also just a part of T-duality. T-duality is the symmetry of the complete string theory, so you should be able to find the T-duals of all the fields in the theory. But that's still, as far as I know, an open question. Okay, so I think this finishes my account of T-duality. So I now want to start with, oh, maybe I just want to give you an example. So I claimed that that my submersion stuff was useful in this context, so let me just give you an example, if I can find it. Okay, so my example is a T-dual of a nil manifold, or it's usually called the Heisenberg manifold, which can be written as R3 over the Heisenberg group. So this is a slight generalization of a, well, maybe H is confusing. Let's call it M, nil manifold, where H is the Heisenberg group. So this is a circle bundle over the 2 torus. Yeah, so submersion going with this one is R3 to N, where you divide it not by Z3, but you divide it by the Heisenberg group. Let me just give you, so the circle bundles over 2 torus are classified by integers. So this Heisenberg group is labeled by an integer. So maybe I should say, so this is the data here are 2 form on the base. So the base is a 2 torus. And the bundle is this nil manifold. So let me say I take a K class there, so corresponding to Heisenberg group HK, and I take an L class here. So let me write out these things explicitly in terms of my submersion code chains.
Just the words with Heisenberg.
Yeah. I will do some group theory later, so I will introduce the Heisenberg group, but maybe in the next hour. Is that okay? Now maybe I can say something about this equivalence. No, I'll do that next hour. Anyway, I just want to show you the formula. So the 2 form in the RAM cohomology, which gives the curvature of that bundle, is just K times this thing. That shouldn't come as a surprise. This is the volume form on the base, on the 2 torus. But now you can explicitly solve for this zigzagging. Log G minus K, and here's a class in my submersion code chains. And H is L. Well, so again, I'm not going to, this is just L times the volume form, that's the generator of H3. For B, you get X dy dz minus 1/2. So this is all really explicit. C would give you minus L del X cup Y cup dz plus 1/2 KL cup X cup dy. And, well, a lengthy formula for H, which I won't write down, but you can check that these things satisfy the zigzag relation, and that the H here is actually, well, this is actually integer class. That's why you need these correction terms. And if you apply my duality formulas, which I've erased, the dual is just interchanging K and L. So you apply these formulas on F hat, A hat, etc., on H hat, B hat, and you find that in these formulas it just interchanges K and L. So that's really, really explicit. And you see that, I mean, if I would describe this in terms of open sets, I would have to give C on all these open sets. Well, here this notation is much more compact. So I will tell you what the Heisenberg group is, but I need a bit more of an introduction into group cohomology first. So I think we can take a break now. Do you still want to do a break?
As you like.
Yeah, maybe we'll do 5 minutes.
Yes, whenever you like.
Yeah, now's a good time.
Please take your friends and colleagues. The school ends tomorrow with the lunch, as we always.
Yep, okay. So I want to now talk about a bit of group cohomology and how to relate, or how to use group cohomology to do some of the computations that I've shown. And I'm not sure how far I'll get, so maybe some of it is a bit sketchy. But maybe I should give you some motivation. So instead of tori or torus bundles, there's also some interest in orbifolds, and the simplest kind of orbifolds are where these are called global toroidal, is where you have a global symmetry, G, that acts on the torus. And yeah, well, in general, this is not a manifold, but this is called an orbifold. And you might be interested in calculating or see how T-duality acts in such a situation. So you might want to see how it acts on these on appropriately defined cohomology groups on these orbifolds. So there exists a standard definition of what orbifold cohomology is. It's just a G equivariant cohomology of, well, let's replace T by X. It's just the equivariant cohomology of X, and there's different ways of calculating such equivariant cohomology. The standard sort of definition is through classifying spaces. So if you have a classifying space B of G and its universal cover, then this is the definition really of equivariant cohomology. Problem doing anything like I've done before on such a space is difficult because the space is infinite dimensional in general. So there's various situations in which this simplifies. So if X is contractible, so first of all, it's sort of, what happens here is sort of mixes the manifold structure with the group structure. And if you want to do computation, would be much nicer to be able to describe everything in just in terms of groups. So if X is contractible, well then this cohomology is just isomorphic to the, well then you can just get EG over G, which is the classifying space B of G, so then it's just a cohomology of B of G, which is one of the definitions of group cohomology. So now I'm running into notational things. This is cohomology of a manifold, and this is the cohomology of the group G. So I don't know how to distinguish them. Maybe I should say H bar. I'm not going to put H bar later on, but. And if G acts freely, and since E of G is contractible, then this is just isomorphic to H of the manifold X over G. But there's actually another case, and that applies to the torus, as well as nil manifolds. This turns out to be isomorphic to the group cohomology of Zn, semi-direct product of G. So you can actually calculate the cohomology of a toroidal orbifold through group cohomology. Maybe I should put H bar for group cohomology. So I want to give you an indication why that's true. But in order to do that, I need to formulate the cohomology of the torus in terms of the cohomology of the group Zn. So I need to tell you a little bit about group cohomology, because I'm assuming that not many people have it in their heads what group cohomology is. Okay. So unfortunately, there's different ways of defining group cohomology. I've given you one sort of definition already, but if you want to have it in terms of explicit differentials and explicit cochains, so I want to define what the, say the group cohomology with coefficients in a module, how that's defined. And this module can either be a left module or a right module. So the differential is different depending on whether it's a left or right module. And then for, say, a left module, there's even two definitions. So there's a definition in terms of homogeneous cochains. So a left module. So these are maps from Gn+1 to the module, which are homogeneous in the sense that if I take the left multiplication by an element of element G in the group, that this is the left action on G0 to Gn. So this takes values in the module, this is the left action on the module, and this is the homogeneous equation. There's also another description of this cohomology, which acts on different cochains. And here the cochains are just maps from Gn to ML. but with a different differential. So let me, for completeness, maybe tell you what the differentials are. So whenever you start doing computations, you sort of use whatever description turns out to be more convenient. So the differential for homogeneous cochains looks very much like the differential in check cohomology or submersion cohomology. So I need to give you what it is in G0 to Gn plus 1. And this, well, shouldn't come as a surprise if I told you that it's the same thing, essentially. So this is the alternating sum where you just leave out the ith entry. So indeed this is probably the most convenient form if you want to compare this cohomology to submersion cohomology. The left one is, but I mean the downside of it is that you work with very particular cochains which satisfy this homogeneity condition, so that might be difficult to pin down. Well, this formula is, so this acts on n plus 1 elements. So for left modules, I take G1 acting on F where I take out the G1. And then I have an alternating sum, IS1 to n, so this is just the first term, which I've separated here just to G0, not G1, sorry. I labeled it different in my notes, so maybe I should make a change here. G1 up to Gi minus 1, and then have the Gi multiplied by the Gi plus 1. And then you go with the Gi plus 2 up to the Gn plus 1. So here you have all the terms, G1 to Gn plus 1, but in the ith entry you multiply the Gi with the Gi plus 1. And then there's a final term, minus 1 to the n plus 1, f G1, where the last entry drops out. So the first and the last term is where either the first entry drops out or the last entry drops out. If for left modules you have the first entry is going to act as a left module. If I would do the same thing for right modules, I have a similar formula, but then the last term acts on the last term that drops out acts on F as a right module. Okay. Now I could write down the explicit isomorphisms between these cochains and therefore between the cohomologies, but I won't do that. I won't be using that much detail anyway. But I just want to formulate a theorem. So if you have a principal bundle, then I claim then there exists an isomorphism between the submersion cohomology, so this is a submersion, say with coefficients in, well, more general, yeah, let's say F, so Z or U1 or R, and the group cohomology of G with coefficients in a left module, and that left module is continuous or smooth functions from P to F. So you can relate the submersion cohomology in the case of principal bundles to just group cohomology with particular modules. And the proof is not that hard. And I'm going to use the homogeneous description to prove that. So the statement, yeah, so if you have something in the, say, P0 to Pk in the fibered product, which I need for for the co-chains on the left-hand side. So that means that the pi of P0, etc., pi of Pk is all equal to some element in the base. And because of the fact that it's a principal bundle, the P0 to Pk are all in the fiber over X. So if you choose a particular P in P, such that pi of P is in the fiber over X, then all the Pi's are given uniquely by P times the right action of some Gi. That's the statement of a principal bundle. So now the map is just going to be given by, well, so I need to take an F here. So G0 to Gk, and this needs to be end up in a module, so it needs to be a function of P, and you obviously just define it as f of Pg0, Pg1 up to Pg. Okay. So really there's, I mean, the map is quite straightforward in this homogeneous representation. It looks more complicated in the other presentations of group cohomology, but it's sort of obvious that if you have a principal bundle, that once you choose a particular point in the fiber, that all the other points are given by group action, so it's a co-cycle. A co-chain should just be a co-chain depending on group elements. So you need to check that this is homogeneous. So tau f is homogeneous. Maybe I won't write it down, but it's sort of obvious if I... so the statement should be, if I'm left multiply by a fixed g, so if I multiply here by a fixed g, then I get this one where p is just multiplied by g times g0. So that's the same as this thing over here in the point p times g. And that's precisely the left action on these functions. So that's precisely, so the thing is precisely homogeneous. Okay, so there's a relation, an isomorphism, and I claim, in fact, which I won't prove, but is if you do this for the torus, or even the nil manifold. So if you take submersion cohomology for the torus, and let me apply this to coefficients in Z, and this is isomorphic to the group cohomology of Zn Z. That's the statement over there. Okay, if I take coefficient Z, then these need to be continuous functions into Z, so they need to be locally constant. So that's why this simplifies in that case. And, well, it's actually a well-known theorem that this group cohomology is actually isomorphic to the group cohomology of the torus. Which, I mean, as I said, it's a well-known theorem. It takes a bit to prove it, but I'll skip the proof. But in any case, for the torus, the submersion cohomology can be written completely in terms of group cohomology. So now I need to do two things to get to my cohomology of orbifolds. So I need to tell you a little bit about central extensions. So two definitions. One is central extensions and the other semi-dark products. So the central extensions are going to correspond to circle bundles. So a central extension, well, let's do it over Z. So a central extension of a group, of a group G by Z, so that you can generalize this to abelian groups, is an exact sequence so let me call the central extension gamma 1 Z gamma G, such that the multiplication on gamma, so gamma can be written, an element here can be written as a pair of element in G and an element in Z, and the multiplication is, well, the multiplication is just the multiplication. So this is an abelian group, T1 plus T2. I'll change the notation. Okay. Well, if I write the group multiplication here as multiplicative, oh no, sorry, I'm going to use the notation in my notes, so sorry for that. So G is just the ordinary multiplication, but the multiplication on Z, which is writing as addition, gets an additional term depending on G1 and G2. Okay. So I don't know if you all saw central extensions, but this is the general definition for a central extension by Z. And you can check that this is associative, well, is associative if and only if this C is a group 2 cocycle. Well, this is actually probably in the homogeneous, in the left representation. So the group 2 cocycle, yes, homogeneous. Okay, that you can just check. Just write out what associativity means, and you'll find some condition on C, and you see that that's precisely a condition of a cocycle. So these cocycles are actually given by elements. So there's also an equivalence relation by splitting this sequence. So these central extensions modulo equivalents are given by an element, or are classified by an element of the second cohomology group. Which, by the way, is the same as, if G is Zn, it's the same as line bundles or circle bundles over the torus, which is what I wanted. Okay, and the other piece of information which I need is okay, now this one, theorem. So I've now replaced the so I claim these correspond to circle bundles. Now my T-duality was based on, for instance, Giesen sequences for circle bundles. It turns out there exists a Giesen sequence for group cohomology as well, which is due to Hochschild and Serre, which is just a long exact sequence corresponding to this situation. So G of Z, H, sorry. So just pull back. There's a term, a map which corresponds to integrating over the fiber, but it has an analog in group cohomology. And then there's the cup product with C, the cup product for group cochains, which I won't write down. It has the same form as we've seen before. Anyway, so there exists such an exact sequence. So once I have formulated my situation, my circle bundles in terms of just groups, I can do my T-duality just on the Giesen sequence for those group cohomologies. Okay, the other little ingredient that I need is,
Sorry, you said very quickly that H2G of this is the group cohomology, right?
yes,
And then it is related to the H3 of GZ of G is a manifold. All right.
line bundles or principal circle bundles. Are classified by the H2 of M. Its coefficient
Right.
Z.
But isn't it true that H2 of G is a so if G is Lie group, H2 of G of Z is 0 for any Lie group.
That's correct, but I'm working with finite groups.
But I think as a group of cohomology, H2 of GZ is related to H3 of GZ when G is considered as a manifold. Because there's that delooping.
I'm going to apply this to G, where G are discrete groups. Yeah, for Lie groups there are no central extension. Okay, the other definition which I need is a semi-direct product. Okay, so semi-direct products of groups N and G is given by some action of G on N. So you need an automorphism of G, map from G, a homomorphism of groups, which maps the group G to the automorphisms of N. So let's say the phi of, let's say G maps to some automorphism phi of G. Then a semi-direct product is given by the following formula G1 on N2. So you don't compose N1 and N2 as you had in the group N, but you can decompose them together with the automorphism, and then G1, G2. Okay. Okay, so I'm getting close to where I want to be. So I want to apply this to where N is, well, I want to apply this to something where N is Rn. N is Zn. And I want to take an automorphism. So I want to apply this to the case where I, nil manifold, no, hang on. I'm confusing my N with a nil manifold and this group. I shouldn't do that. Anyway. So I want to choose as an automorphism where I, where I let these groups act on a vector space V, which is Rn in my case. So this needs to be an automorphism of Rn, so an n by n matrix. And then we have a representation and G on Rn, which is phi G on V plus n. So again, what I'm trying to do here is I have Rn, I have my surjective submersion, which has an action of Zn, and I also now have an action of G on Tn, which I want to lift over here. And what I claim is that action is actually an action of, well, of Zn semi-direct product G. So in some sense, Rn divided by this action of Zn is going to be what I would like to call the toroidal orbifold. Okay, so it's straightforward. The action on V is just given by this matrix, which, well, element of GL and R, but I also have an identification here, modulo Z, modulo Zn, which is this identification. But if you combine it two, you actually see that this action defines an action of the semi-direct product. Because if you do this twice, then, well, you see you're going to, one of the vectors is already shifted by this automorphism. So you find precisely that relation. If you don't see it, then that's an exercise. Okay, so this hopefully convinced you that if I want to do T-duality for global toroidal orbifolds, then the proper setup is to look at the cohomology of, well, of Zn, semi-direct product of G, and to try to apply my T-duality techniques over here, in particular make use of the Giesing sequence, etc. So I'm not going to actually give you examples, I think. So instead of the torus, you could also take a nil manifold here and do the corresponding stuff. So this actually gives you, say, I mean, it's quite easy to do explicit computations with these groups, much easier than working with classifying spaces. For instance, you can compute the cohomology of this group through a spectral sequence. It turns out that the second term in the spectral sequence, I'm not going to tell you what a spectral sequence is just the iterated cohomology of G with coefficients in Z and Z. And this converges to that, well, in almost all cases it collapses at the second term, so this cohomology is actually isomorphic to an iterated cohomology, and this map actually can be written down very explicitly. Now this is just the standard cohomology of Zn that's very well known, its representatives are very well known, and then for a lot of finite groups you can just find explicit representatives with coefficients in that G module, and then you can apply this map explicitly and get explicit formulas for co-cycles here. That's really very straightforward. So you can do all these T-duality things, which I've given you one example for the three-dimensional nil manifold, but you can do them for toroidal orbifolds in almost exactly the same way. And yeah, so the spectral sequence is called the Hochschild, the Linden Hochschild. Again, this is stuff from the 50s, I think, last century. But again, these iterated cohomologies are very easy to compute, so this gives you a very nice machinery to do all of these computations. So I didn't explicitly tell you what the Heisenberg group was yet, but the Heisenberg group is the central extension of Z2 by Z. So the formula are explicitly there if you want to calculate what the multiplication is on the Heisenberg group. But you can think of it, the nil manifold corresponding to it would be parameterized by 3 coordinates. and you get the corresponding product rules. Okay. Yeah, so one more remark. So this is just the topological part of it. If you want to do it on differential forms, on these zigzag things, then you need to find an action of the finite group G on this B field, this H field, etc. So that means that you look for an equivariant structure. So that you can do as well, and you can do the T-duality rules in the same way as I've done them in my particular example. So I'm not going to write out any example here, I think. But I hope the idea is sort of clear. So yeah, I think this concludes my lectures. I hope, at the very least, I hope I've convinced you that if you do a computation with open covers, that you might as well look at different ways of doing that in terms of surjective submersions. It might be very much easier. Of course, you need to find the appropriate surjective submersion that does for you what you want to do. But for the torus, it's all very straightforward. So, so if you're ever interested in doing particular concrete computations of T-duality or the related mirror symmetry, then this is a very good machinery to use, I think. Thank you. Finished early, as I promised.
So the questions or comments? So I have a question because what you explained in this last blackboard, so it concerns really, so you can do the differential cohomology, structure on all this.
So, yeah, so if I want to have an equivariant as one bundle, then I need to have these, this exact thing, and I need to define an action of the group on these fields. And that goes with zigzagging in a triple complex of the del of the RAM and of the group cohomology differential. So that's why I didn't really want to write out anything, because it becomes just a complicated three-dimensional mess. But yeah, you need to define action of the finite group on these fields so that you get an equivariant structure. And you'll find that those equivariant structures are, well, in the case of the connection and the curvature, are given by this, are classified to isomorphism by the second cohomology group of this semi-direct product. As it should be, right? I mean, this classifies line bundles, so well, it classifies the F, but these, if you want to have the equivariant structure, you need to look at second cohomology of that group. And you can calculate, well, and so the H3 gives you the H, B, C fields, and you can just look at the Giesen sequence for this particular group to see how the T-duality works. Yeah, so it works nice for tori or nil manifolds, but yeah, for more general orbifolds, you'd have to find the appropriate submersion that does what you want. But I mean, I think the whole idea that you can write the cohomology over the integers explicitly in something which looks like just a de Rham calculus, but then over the integers is sort of amazing in my view. You don't have to specify things on all the open sets and overlaps. I just work with the single symbol, and it does everything what I need.
Yes, I understand it's much easier. many calculations are doing without saying it explicitly, but in this.
Yeah.
Great.
Yeah. Yeah, it's a very nice calculus.
So, thank you again.
Okay.